Okay, this is problem B from the October 12th, 15th practice problems. And so in terms of this question, we are to determine with these two molecules, are they the same, but they're not meso compounds? So are they the same compound and it's not meso? Are they the same, but are they the same meso compound? Are they enantiomers or are they diastereomers? So when you have two chiral centers, initially maybe all four of these choices are in play. But the first thing that we have to do here is we have to determine whether or not these molecules could be meso. And what do I mean by could they be meso? Well, if you have a Fisher projection and you have the same three groups on the top carbon that you have on the bottom carbon, they could be meso. Or each molecule could be meso. Now, so that's the first thing you have to do, is you have to check, are these three groups attached to the top carbon, are they the same as the three groups attached to the bottom carbon? And if that's the case, then you have to begin to rotate the Fisher projection in order to try and line the groups up like this, where you have a mirror plane between the three groups. And if that's the case, then the molecule is definitely meso. If, on the other hand, you can line up two of the groups, but then the other groups won't line up, then this would be not meso. And in a Fisher projection, basically you have a Newman projection sideways, so that you are able to rotate these groups around the top or around the bottom in order to interchange the group. So you're allowed that free rotation. Now in this case, group switching will not work. If both of these molecules are the same meso compound, group switching won't tell you that. If these are the same group or same meso compound, determining R and S will not work. So the way we have to approach this problem is that we have to first of all determine, are these two molecules meso? Are they meso? So let's take them one at a time here. So if I look at the molecule on the left, first of all, I've got chlorine, hydrogen, oxygen, chlorine, hydrogen, oxygen, so it fits the first test. The same three groups are attached to the top and bottom carbon. Same thing over here, chlorine, hydrogen, oxygen, or OH group, chlorine, hydrogen, oxygen group there. So now what I have to do is for the left molecule, is it meso? Well, let's try and line up the hydrogen groups. So let's say I rotate this hydrogen back here, the chlorine there, and the OH there. Okay, if I do that for the top carbon, the H goes here, the chlorine goes here, and the OH goes on the other side. So all I did was rotate H into Cl, Cl into OH, OH into H. Now the bottom carbon stays the same. Is it meso? Yes, because there's the mirror plane. So the left-hand molecule is meso. How about the right-hand molecule? Let's try and line up the H groups. Only down here, let's move the H here, the OH group there, the Cl over here. The top carbon, I'm going to write its configuration. I didn't do anything to it. The bottom carbon, I'm going to move the H down to the Bottom position, the OH to the right, and the Cl over here to the left. Mirror plane, yes, it's meso. So these two molecules then are the same meso compound. And that's my answer. Okay, so that's one possibility, is that you would end up with the same molecule, and it's the same molecule because they both are meso. But let me go through a little bit here and try some of the other possibilities and show you what they would look like. So for instance, let's go ClHOH. So let me write the first let's go ClHOH, and let me go ahead and put OH, Cl, and H. And then over here, let me go H, Cl, OH, OH, H, and Cl. So now let's compare these two molecules. So again, when I look at this, I immediately see that the top three groups are the same as the bottom three groups, which means I should check each one to see if they are meso. Okay, now in this case, let's go ahead and look at the left molecule, and I can immediately tell it's not meso. How can I do that? Well, because in the left molecule, the two chlorines are lined up in a mirror plane, but the H's and the OH's don't line up. If you don't believe me, try and line up the H's, and you'll see that the H and the Cl's don't line up. So this molecule is not meso. Let's try the right-hand molecule. So let me bring the H down here, the OH over there, the Cl over there, and of course if I do that, my top carbon stays the same. My H comes down, my OH goes to the right, my Cl is there. Mirror plane, yes, this is meso. So what's the relationship then when one of the molecules is not meso, but the other molecule is meso? Well, now in order to determine that relationship, we need to compare the two carbons on the top, the two carbons on the bottom, and determine, are they the same or opposite for each one of the pairings. So in order to make this a little bit clearer, I'm just going to rewrite the left and the rotated right molecule side by side so I can do this comparison. Okay. Let's look at the two top carbons. Are the two top carbons the same configuration, or are they opposite configuration? Well, in the video for the practice problems from October 12th, 15th, problem A, I showed you how to do this comparison by three different methods. So one of our first methods is we could try and line up the groups. If I tried to line up the groups, I could bring the H down here, I could bring the Cl over here, and I could bring the OH up there. So I'm just going to circle the groups after they've been rotated. Does the left-hand carbon and the right-hand carbon match up? Well, the bottom carbon is the same in both cases. I have lined up the two hydrogens, but I did not line up the chlorine and the OH. So two of the groups, including the bottom carbons, lined up. The Cl and OH didn't, so that means two aligned, two didn't. So the top carbon has the opposite configuration. Okay, they are opposite each other. I could do this by group switching. So if I did this by group switching, let me erase this. And now for group switching, let's do the following. Let's switch the H and the Cl to try and line up the left top carbon with the right one. There's one switch. Are we aligned? Yes. In an odd number of switches, what happened? That means those two configurations of those carbons are opposite. So the top carbon has the opposite configuration in the two molecules. Okay. Now let me show you one other comparison that you can make. Let's say that for the top carbon I rotate the OH over here, the Cl up here, and the H over here. Now, if you look at the top carbon, do you see the mirror plane between the OHs, between the Cls, and between the H's? Do you see the mirror plane there? Again, chiral carbons that are mirror plane images have opposite configuration. So no matter what way we do this, we find that the top carbon has the opposite configuration in both of these molecules. And I just want to, okay, so now let's do the same thing for the bottom carbon. And for the bottom carbon, I don't see a mirror plane right off the bat. I don't see anything lined up, but let's see. Can I align these groups to be the same? Let's say I bring the H up here, I bring the OH over here, and I bring the Cl down here. Now the Cl's line up, the OHs line up, and the H's line up. So the bottom carbon has what? The same configuration. Okay. Let me erase those, and let's do this by group switching. Okay, I want to turn the left molecule into the right molecule by group switching. How many switches is it going to take? Well, let's switch I need to switch the OH and the Cl. So there's one switch, and that lines up the Cls. And now I need to do an HOH switch. So now I have if I do the H and OH switch, I now have the OHs lined up and I have the H's lined up. So it took me two switches to go from left to right to align those. Two switches means an even number. That means those bottom carbons have the same configuration. Okay. So I have to look at each carbon and determine, are they the same or do they have the opposite configuration? Okay. So what I found is that in this case, the top carbon has the opposite configuration, the bottom carbon has the same configuration. At least one chiral center is opposite. At least one chiral center is the same. What's the relationship between these molecules? They are diastereomers. So let's take a step back. I originally found that this one was not meso and this was meso. Whenever you have a situation where you find that you have not meso and meso, what's the relationship going to be? The relationship is going to be that they are diastereomers. And the analysis we went through to determine that the two top carbons were opposite and the two bottom carbons are the same is what you would do for any Fisher projection when you're trying to look at two Fisher projections and determine, are they the same? Are they the same and not meso, same and meso, diastereomers, or enantiomers? Okay. What would happen if they were both not meso? If they were both not meso, then you would have to do this analysis and determine whether the two top carbons were the same or opposite, determine the two bottom carbons are same or opposite, and in that case your choices are going to be pretty straightforward. If both carbons are the same, it's the same compound, but since they started out not being meso, they're not meso. If, on the other hand, both of the carbons were opposite and they were not meso to begin with, they would be enantiomers. So this approach of looking at top and bottom carbons, or any carbons, to determine, okay, are these carbons opposite, are they the same? That's what we use to determine whether a molecule, two molecules are same. Not meso. If they're not meso, then they're either the same, not meso, or they are enantiomers, or they are diastereomers.